It is a great pleasure to be here at this Google Zeitgeist meeting. Some time ago, I wrote a popular book, A Brief History of Time. The book described my picture of the universe, but it left a number of issues unresolved. I have therefore written a new book, The Grand Design, with Leonard Mlodinov, to try to answer questions like, how can we understand the world in which we find ourselves? What is the nature of reality? How does the universe behave, and why does it exist? Does it need a creator? Most of us don't worry about these questions most of the time. But almost all of us must sometimes wonder, why are we here? Where do we come from? Traditionally, these are questions for philosophy, but philosophy is dead. Philosophers have not kept up with modern developments in science, particularly physics. Scientists have become the bearers of the torch of discovery in our quest for knowledge. The purpose of the grand design is to give the answers that are suggested by recent discoveries. They lead us to a new and very different picture of the universe and our place in it. In the book, we describe how regularities in the motion of astronomical bodies, like the sun, moon, and the planets, suggested that they were governed by fixed laws, rather than being subject to the arbitrary whims and caprices of gods and demons. At first, the existence of such laws became apparent only in astronomy, or astrology, which was regarded as much the same. The behavior of things on Earth is so complicated, and subject to so many influences, that early civilizations were unable to discern any clear patterns or laws governing these phenomena. Gradually, however, new laws were discovered in areas other than astronomy. This led to the idea of scientific determinism. Given the state of the universe at a specific time, there must be a set of laws that would specify how the universe would develop from that time forward. These laws should hold everywhere, and at all times, otherwise they wouldn't be laws. There could be no exceptions, or miracles. Gods or demons couldn't intervene in the running of the universe. The laws of science describe how the universe behaves, but to understand the universe at the deepest level, we also need to understand why. Why is there something rather than nothing? Why do we exist? Why this particular set of laws, and not some other? I believe the answer to all these questions is M-theory. M-theory is the only unified theory which has all the properties that we think the final theory ought to have. It is not a theory in the usual sense, but it is a whole family of different theories, each of which is a good description of observations only in some range of physical situations. It is a bit like a map. As is well known, one cannot show the whole of the Earth's surface on a single map. The usual Mercator projection used for maps of the world makes areas appear larger and larger in the far north and south, and doesn't cover the north and south poles. Instead, one has to use a collection of maps, each of which covers a limited region. Like Google Earth, the maps overlap each other, and where they do, they show the same landscape. M-theory is similar. The different theories in the M-theory family may look very different, but they can all be regarded as limiting cases of the same underlying theory, when certain quantities, such as the energy or some fields, are small. Each theory has only a limited range of validity, but where the ranges of two theories overlap, they predict the same observations. There is no single theory that is a good representation of observations in all situations. M-theory predicts that a great many universes were created out of nothing. These multiple universes can arise naturally from physical law. They are a prediction of science. Each universe has many possible histories, and many possible states at later times, that is, at times like the present, long after their creation. Most of these states will be quite unlike the universe we observe, and quite unsuitable for the existence of any form of life. Only a very few would allow creatures, like us, to exist. Thus our presence selects out from this vast array only those universes that are compatible with our existence. Although we are puny and insignificant on the scale of the cosmos, this makes us, in a sense, the lords of creation. But I am sure some of you are asking, how do we know M-theory is true? How can you prove it really describes our universe? It might be mathematically elegant, but how can M-theory be tested experimentally? Well, there is some hope that we might see hints of M-theory at the LHC particle accelerator in Geneva. The LHC is the largest, most complex machine in the world, possibly the universe. From an M-theory perspective, it only probes low energies, but we might be lucky and see a weaker signal of fundamental theory, such as supersymmetry. The search goes on, and already some possibilities have been eliminated. However, to directly test M-theory we would need a new LHC capable of achieving enormous energies. It would have to be scaled up to a collider ring, about as large as our galaxy, the Milky Way. This technology is some way off, and I don't think even Google could afford to build it. Testing M-theory is still possible, because there was a time when the highest energies imaginable were actually reached, at the beginning of the universe, in the hot Big Bang. The very early universe is the ultimate laboratory for testing our ideas about the building blocks of space-time and matter. Different theories leave behind different fingerprints in the current structure of the universe, so astrophysical data can give us clues about the unification of all the forces of nature. But the importance of cosmology as an experimental science is a recent development. When I first started out as a graduate student in Cambridge in 1963, the situation was very uncertain. It could be said, then, that a cosmologist was cheaper to fund than a mathematician. A mathematician needed a pencil and paper, and a waste paper bin, but a cosmologist could do without the bin. We could make up any idea we liked, such as the steady-state theory, knowing there was no data to contradict it. All that changed in 1965, with the discovery of the cosmic microwave background radiation. These microwaves are all around us, and they are the same as those in your microwave oven, but much less powerful. They would heat your pizza only to minus 271.3 degrees centigrade. Not much good for defrosting the pizza, let alone cooking it. The only reasonable interpretation of the background is that it is radiation left over from an early very hot and dense state. As the universe expanded, the radiation would have cooled until it is just the faint remnant we observe today. Cosmology took another enormous leap forward in 2003, when the first results from the NASA WMAP satellite were published. WMAP was able to produce a wonderful map of the temperature of the cosmic microwave sky. This is a snapshot, or photograph of the universe, as it was at about 1/100% of its present age. The irregularities you see mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density will slow the expansion of the region, and can eventually cause the region to collapse to form galaxies and stars. So look well at the map of the microwave sky. It is a blueprint for all the structure in the universe. The WMAP data you see here has about 1 million pixels, and it contained so much information, it marked the dawn of a new era. Cosmology became a precision science. For the first time, cosmological parameters could be measured to within a few percent, and we could start in earnest testing our theories about the origin of the universe. The hot Big Bang model has become so well attested and quantitative that it is now called the standard cosmology. It describes a seamless history, from the first fractions of a second after the Big Bang, through to the present day, 13.7 billion years later, from the synthesis of nuclei and the formation of atoms, through to the collapse of galaxies. And we are trying to push this understanding further backwards in time. At the LHC, we are testing physical laws, which describe the universe at 1/100th of a nanosecond. But we are even more ambitious than this in cosmology. Through WMAP and other data, we are testing the theory of inflation at about 1 trillion trillionth of a second. The world record for inflation was in Germany, after the First World War. Prices rose by a factor of 10 million in a period of 18 months. But that was nothing compared to inflation in the early universe. Unlike inflation in prices, inflation in the early universe was a very good thing. It produced a very large and uniform universe, just as we observe. However, it would not be completely uniform. The marriage between quantum theory and general relativity means that the universe became slightly irregular. I was one of those who proposed that these quantum fluctuations would become frozen in spacetime and imprinted in the cosmic microwave sky. We worked out all the details in Cambridge in 1982 at a small meeting known as the Nuffield Very Early Universe Workshop. These irregularities are the key quantitative prediction of inflation. The WMAP data has been shown to have exactly the right kind of variations predicted. So we know we are on the right lines. Inflation has successfully matched all the key data to date, but it makes some other truly remarkable predictions. Simple inflation predicts that the primordial irregularities have Gaussian or purely random statistics to 1 part in a million. That is, their distribution very accurately follows a so-called bell curve. Many cosmologists today spend their time investigating this random hypothesis, looking for strange non-random features or correlations in the data. One frivolous example can be seen in this WMAP snapshot. If you zoom in and search carefully, you can just about make out the letters SH. This does not seem very random, especially as these are my initials. However, this is controversial because Australian astronomers look at the universe the other way up. They could claim instead to have found the initials of Homer Simpson. Unfortunately, these features are from an unreliable part of the map contaminated by the Milky Way galaxy. In fact, a careful analysis of the WMAP data has established that the fluctuations are purely random, to 1 part in 10,000. The Planck satellite is the world's most ambitious survey of the cosmic microwave sky. We are using this new data to measure cosmological parameters to sub% accuracy, and we are on the way to testing the random hypothesis to nearly 1 part in 100,000. This is the most stringent test of inflation to date. I will let you know when it passes. Because inflation is such a beautiful idea, I am sure it is right. But what if the universe is not purely random? What if there are some unexpected correlations? Well, this might not be such a bad thing. It would mean the simplest model of inflation is wrong, but there are alternative models of inflation, which are well motivated by fundamental theory. Each of these has a distinctive fingerprint, which could be observed in these non-random correlations. Such fingerprints would be clues about the origin of the universe, and about the unification of the forces of nature, maybe even about M-theory. But Planck is just providing the best data available for now. Ambitious future experiments will supersede it, mapping billions of galaxies so that we can better understand our place in the universe. Perhaps, one day, we will be able to use gravitational waves to look right back into the heart of the Big Bang. Most recent advances in cosmology have been enabled through space technology. From space, the view of our wonderful universe is clear and uninterrupted, and we will depend on it for future progress. I am a great supporter of space exploration, and I am booked to participate in it myself, on one of the first commercial space flights. I have already been through astronaut training in zero gravity. In a time of shrinking government budgets, we are going to need more private enterprise, and individuals taking up challenges like this. I am pleased, for example, that Google has set up the Lunar X Prize to encourage robotic space exploration. I have emphasized that cosmology has emerged as a data-driven field. This deluge of new data has challenged cosmologists to construct increasingly sophisticated mathematical theories, models of such complexity that it is no longer feasible to solve them using pen and paper. We need supercomputers to do the job, systems like the Cosmos supercomputer, at my Center for Theoretical Cosmology in Cambridge. We put our theoretical models on the computer and create mini Big Bangs to predict how the universe might look and to compare with observation. These technologies enable us to reach out and touch the real universe, testing if our ideas are right. Without them we would be mere philosophers, but we don't want to become advanced programmers either. We want to keep our focus firmly on understanding the universe, so we need IT companies to keep these vital tools simple and accessible for us, even if the scale of the problem grows like an inflationary universe. So let me finish by returning to M-theory, and my original question, why are we here? M-theory is the unified theory Einstein was hoping to find. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us in our universe, is a great triumph. But perhaps the true miracle is that abstract considerations of logic lead to a unique theory that predicts and describes a vast universe full of the amazing variety that we see. If the theory is confirmed by observation, it will be the successful conclusion of a search going back more than 3,000 years. We will have found the grand design. Thank you for listening to me.
On behalf of all of us, I want to thank you, Professor Hawking, and I wanted to ask you to have the privilege of one more question. As you know, Google, we recently told the world about our new driverless car, which I'm looking forward to driving around when it's a little more debugged. What is the single most exciting and the single most frightening aspect of a future where artificial intelligence begins to play a much more central role in our lives?
Artificial intelligence will greatly change the future. We need control. There is still a role for human intelligence.
Good. Thank you very, very much. Thank you.